Solving exponential equations. Day 1. Here is the property that we'll be working with today, the property of equality for exponential equations, which states if b is greater than 0 and b cannot be 1, then b to the x equals and b to the y if and only if x equals y. So what that means is if we have the same bases, then we can say that the exponents are the same. And that's that. We had to have that as a property to define that, just like the distributive property, why we can do the things we can do in mathematics. So because the bases here are the same, we know that the exponents are the same, so x equals 2 is our answer. So this is a basic one where we can kind of see that the bases are the same. So if the bases are not the same, then we cannot say the exponents are the same, but we can make the bases the same. And that's when it gets more complicated. So example number 3. So 5 x to the power of x equals 125 to the x power. So now, right now the bases are not the same, but we know that that 125 is a base of 5 and it's 5 to the third power. So what we can do is bring everything down. So now we can use we've got the same bases. Well, they're not quite the same because we have a power to the power, but we can use our power exponents and 5 to the x, bring that down. And our property is multiplying those together. So we get 5 to the 3x, which means, bases are the same. So x equals 3x. Now, the problem here a lot of times is that we need to get the x's together. Now, what I notice sometimes with students at this point is that they try to divide both sides by x. And right now, you don't have a license to divide by x. So this is not the correct way to do that because there are special mathematical properties that we have to deal with if we divide by x. And in doing so, we've broken those rules by dividing by x here, and we don't want the math police to come after us. So to solve this problem, we have to get all the x's on one side. So we will subtract x from both sides, which means the left side is equal to 0, the right side is equal to 2x. We divide both sides by 2, so x equals 0 is actually the number that would work to make these equivalent at the beginning of our problem. Example number 4. 4 to the x power equals 2x minus 2. So in writing down the original problem, a lot of times I look at it and go, what do I notice that they're similar? What do they notice that the commonalities? So the bases are not the same, but the similarities is that I can make 4 into a base of 2. So that would be 2 to the second power for 4 to the power of x. And then we bring down that 2 to the x minus 2 power. Now, same thing we did with the last problem is we can use our property of powers and multiply those two together. So now that the bases are the same, we can use our property of equality for exponential equations to state that because the bases are the same, our exponents are also the same. So we can set those equal to each other. And now we can solve for x. So x equals -2. And what happens is, remember, this is the solution that will make our original equation up here true. So if we substitute -2 in for each of these, then it would be a true statement. So 4 to the negative 2 power should equal 2 to the negative 2 minus 2. So I'm going to move my negative into the denominator to make it positive to do my check to see that it works. 1 over 4 to the second power should equal negative 2. So that would be 2 to the negative 4 power. And 2 to the second power would be 16. And we'll move this negative exponent into the denominator to make it a positive exponent. So 2 to the fourth power would be 4 times 4. That would be 16. So it does check out. For our next example, this one's a little bit trickier. We're on number 5. X plus 2 equals 27x. Now, this one kind of a little bit confuser because of the 9 and the 27. We know that 9 times 3 is 27. So, but the thing is we don't want to pick 9 as our base because it would work nicely for the left-hand side. But if we think about 27, what would that be to the power of 9? How many 9s would I multiply together to get 27? And it's not 9, it's 3, which is a factor of 9. So when we look at this, we want to think, oh, what can we break 27 down into? It's prime factorization, and that's 9, which is 3 times 3, times 3. So let's go to bases of 3. So that would be 3 to the third power for 27. Bring down my power of x, bring down my equals, and 9 would be 3 to the second power. And then that would be to the x plus 2. Now what also makes this a little tricky is that this exponent, it is a group. Now, it's a grouping symbol, but it's not shown because it's all in the exponent. So here's an example of where students make a common error in there when they work with solving exponent equations. So 3, they write down power of 3 or base of 3, 2x plus 2. And what's happening is they're missing the distributive property in the exponent. So that is a group. It's just a hidden grouping symbol, and that 2 was distributed to the first term, but it also gets distributed to the second term. And that's a little bit tricky here at the beginning because we want to remember that these grouping symbols are hidden more often in more complex algebra problems. So this one has to be a 4 plus 4 at the end. Now the one on the right is a little bit easier because there's only one term to multiply. And then now we have the same basis, so we can use our property of equality for exponential equations and setting the exponents equal. 3x, we'll subtract 2x from both sides, and 4 equals x. So what will make this original equation at the beginning true is when x equals 4, it will make both sides true, the same number. Example number 6. 4 to the power of x equals 2 to the x minus 2 power. So we're going to use this one twice and talk about kind of the more different ways we can solve equations in different pathways. So I noticed that there's a 4 and a 2, so our base of 2. So I'll go that way with the base of 2. This one just stays the same, so I bring it down. So power of powers, exponent, would be 2 to the 2x equals 2 to the x minus 2. Now I'll use our new property of equality for exponential equations and set my exponents to equal because the bases are equal now. And we'll subtract x from both sides. So x equals -2. That will make that equation true. So now we're going to think about this in a slightly different way. Same process, same properties, but just a little bit different. So if we think about it, we could go to that base of 2, but we could also go to a base of 4. So that would be 4 to this x power. Now, how would we get a base of 4, but we still need to keep it as a power of 2, or well, 2 is the base, sorry, the base. I'll bring down my power since I'm thinking about it. So this number inside, I want a base of 4, but it has to be a 2. Oh yeah, the square root of 4 is 2. So we can take 4 and put it to the half power, which is the square root of 4, which is equal to 2. So now that we have our base, we've got our exponent to a power. Now this is that remembering we need to distribute because that x minus 2 is a group, and we need to make sure that we distribute that 1/2 to both of those. So 4 to the x power equals 4 to the 1/2 x minus 1. Now we can use our property to, the bases are the same, then the exponents will be equal. Bring those down and solve for x minus 1/2 x from both sides. So 1/2 x equals -1. We'll multiply both sides by 2 to cancel out that fraction. So x equals -2. And we got that same answer, which we should have. If I got something different, I would look at where I made an error, probably up in this distributive property here. But we can use either base. So if you start to go with the 4, you have all the concepts to work with that at this point, now that you know what the fractional exponents mean. So we'll move on to base 10. So if we have a base 10, which I kind of like because that's our counting system, times 10 to the x power equal, there's the equals, 1/10. So now we're looking at a little bit more complex, but because we have the same bases over here, I can add those exponents. So -3x plus x is 10 to the -2x on the left-hand side. And, I would like to have that base of 10, so I'm going to move it up. So I have a base of 10, but then with my exponent of 1 here, if I move it up to the numerator, it's going to be a -1. So I can kind of work with that to get my bases the same. That was my goal, to kind of get those the same base numbers. That means our property we can use that the exponents are the same. So -2x equals -1. We'll multiply both sides by a -1/2. Multiplied by -1/2. I had to think about that. I was going to do a times 2, but I needed to cancel those out. So x equals a +1/2. So when x is 1/2 up here, so that means 1/2 here and a 1/2 here would make both sides equal to 1/10. Our last problem we have is a base 4 x plus 1 equals 1 over 64. So now we can use a couple of different problems, like a different thinking problem here. We could use a base 2, or I'm thinking a base 4, or we could do a base 16. And so these are kind of where it's getting a little bit more complicated, but what we can do is we can think about, well, what's the easiest? I'm thinking 4, base of 4. So I'll keep the left-hand side. I'll change my fraction 1, the 64 part, into a base of 4. So 4 times 4 is 16. 16 times 4 is 64. So that would be to the power of 3. Yes, 3264. Now I want to, it's not quite a base of 4 yet. I mean, the denominator is, but I'd like to be in the numerator. So I'm going to take and move that denominator up, and 4 to the negative 3 power will be equivalent. Now that the bases are the same, I can set the exponents equal. X plus 1 equals negative 3. Subtract 1 from both sides. And we got to be careful with the calculation. X equals negative 4. So when we substitute negative 4 in for x, it will make this equation true. And that is solving exponential equations.